So to review our circle stuff, pieces of the circle that are important to us. Oops. This, of course, is called a diameter, assuming that goes through the center. This one's actually goes through, we're going to call a reference diameter. Generally, a reference diameter is a horizontal diameter. You can, in certain cases, use a vertical diameter as a reference diameter. That's usually called a co-reference diameter. You'll understand why it's called a co-reference diameter after a few more days of class. It's the reference diameter for the complements, yes. A structure that touches the circle in exactly one spot but never enters into the circle is called a tangent. A structure that actually does cut through the circle, technical definition is it contains some points inside and some points outside the circle, is called a secant. And the one that most people don't realize is a piece of the circle, and it's a property of any point. I can pick any point on the circle. Tell me when to stop. So there's a point on the circle. The distance from that point to the reference diameter is called a sign. Every point on the circle has a sign. Like this point has a bigger sign. This point has a littler sign. Every point on the circle has a sign. The distance from that point to the reference diameter. Very good. What about right here? That's an endpoint of that reference diameter. It still has a sign. The sign is 0. So what we're going to talk about today is something called the unit circle. The unit circle is a circle that has a radius of 1 unit. We talked about this when we did our radian measure too, a circle with a radius of 1. Our unit circle is centered on an axis. So the center of the axis is the center of the circle. This is our 0 degree point, just like we talked about before, and we go around counterclockwise. 90 degrees, 180 degrees, and so on. This right here is referred to as the initial side, because that's where all angles start. It's right there. And of course, they will go around counterclockwise. So right there, that's our angle. We'll call that angle theta. Again, that's the Greek letter theta, looks like that. It's just like X or Y or Z. It just represents an unknown angle, any angle. This blue line is referred to as the terminal side. That's where the angle stops. That's the end of that rotation. Remember, you think of angles as being a rotation. You start on the initial side, you end on the terminal side. That terminal side defines a point on that circle. And that point has a sign. The length of that segment, or that distance of that, the sign of that point is defined to be the sine of that angle. So the sine of theta is just the distance from that point on the circle down to the reference diameter. A tangent touches the circle as we saw up above. Well, for our trig functions, it touches the circle at the reference diameter. So this point right here, it's going to extend up or down to that terminal side. Well, how do we know where to stop up here? We extend that terminal side until it hits that tangent. So that purple length is the tangent. of that angle theta. And then where we extended that diameter, or sorry, not the diameter, where we extended that radius out there, I should say, to meet the tangent, that length is the secant of our angle. And those are our three main trig functions: sine, tangent, come on, and secant. Those are the three main trig functions. Well, you might be thinking, well, I've always heard sine, tangent, and cosine. We'll show you where the cosine fits into all this. These main trig functions, by the way, as this angle gets larger, from 0 up to 90 at least, as the angle gets larger, as theta gets larger, does sine get larger or smaller? Yeah, it's going to get bigger, right? If the angle gets bigger, it's going to move from here up to like here. That's longer, isn't it? So sine gets larger. Would the tangent get larger or smaller? Larger, yeah. As that terminal side moves up, this is going to have to reach further and further and further to get up to it, isn't it? So the tangent gets larger. Well, the secant get larger or smaller? Larger. It's going to have to reach further up here to meet the tangent, isn't it? All of our main functions, from 0 degrees to 90 degrees at least, as the angle gets larger from 0 to 90, all the values of those main functions get larger from 0 to 90. Very good question. What's the tangent at 90 degrees? Let's draw out a little miniature circle here for that. First of all, what's the sine at 90 degrees? Yeah, it's just the radius, which is 1. Yep. Sine of 90 equals 1. Tangent goes here and extends up until they intersect. Well, the tangent and this terminal side, what can we say about them there at 90 degrees? They're parallel. Will they ever intersect? No. Tangent of 90 degrees is undefined. How about the secant? It's also undefined because it has to intersect the tangent to be defined. So at 90 degrees, the tangent and the secant are parallel, so they're both undefined. They have to intersect to define each other. So what about that thing we referred to as the cosine? Well, cosine is actually a modified word. It has a prefix. It's actually co, the prefix co, and then the word sine. This sign is just that sign. So what does the prefix co stand for? Of the complement. Come on now. This cosine literally means the sine of the complementary angle. So if I want to find the cosine of theta, this is theta. Where would its complement be? Right there, right? Yeah, that's 90 degrees. That's its complement. Well, the sine of the complement, the sine would have to go like that. It would use, that's why we called this the co-reference angle. The cosine goes off to that reference diameter, or the co-reference diameter, I should say. So there's the cosine. Now what we can do is we can just bring that down here and say this distance is the cosine of theta. But it really is that distance up here, this one up here. And now, of course, that then brings us to our cotangent, would be the tangent from the co-reference diameter. And the cosecant then is the, if we extend that terminal side out to intersect the cotangent. So you can see there's actually like 4 triangles formed there. Those triangles actually define our trig functions. So I'm going to come down here. I'm going to draw a circle. The first triangle I'm going to look at is this one right here. What's that length of that radius? 1. What's this side called? That's the sine of theta, if this is theta. From here to here is the cosine of theta. Now, let's say I'm going to draw another triangle. I'm going to tell you that this is a right angle here. I'm going to tell you that this angle is theta. What can I say about those 2 triangles? They're similar. Very good. Because if I know that 2 of the angles are equal, the third angle has to be equal. So that similar just means all 3 angles are equal for triangles. Now in this right triangle, I'm going to name my sides. This side here is what we always called the hypotenuse, right? The other sides are named depending on what angle we have. Well, we have this angle. Those other 2 sides are legs. One of them is referred to as the adjacent leg. Adjacent means next to or touching. Which leg touches the angle we're looking at? The bottom. That's the adjacent leg. We usually don't use the word leg there anymore. We just say adjacent side, but it is the adjacent leg. Well, then the only one left is this one here. It's across from the angle we're looking at or opposite it. That is the opposite leg. Now, if I want to define the sine of an angle, I'm going to use this triangle here, sine theta, and I'm going to compare it back to its hypotenuse, which has a length of what? 1. In my other triangle, what side corresponds to the sine here? Opposite side. What side corresponds to the 1 here? Hypotenuse does. So that is just from the similar triangle. The sine of theta from the circle compares to 1 in the same way that the opposite side compares to the hypotenuse for any triangle that has that same angle theta in it. Any right triangle that has that angle theta in it. Let's look at the cosine down there. We're going to compare that back to its own hypotenuse of 1. What side of the other triangle corresponds to the cosine? The adjacent side. What side of that triangle still corresponds to the 1? The hypotenuse. So in any triangle that has that angle theta, the cosine is going to be equal to the ratio of the adjacent side divided by the hypotenuse. Keep those 2 written down somewhere. I would actually recommend you take like a back cover of your notebook or last page of your notebook or something and write those down because you're going to need to reference them a lot. I'll pause even for you so you got time to get it written down the way you want. That's where we're going next. Draw your circle again. Pretend that looks round. We're going to have our lovely angle theta in here again. But this time we're going to put the tangent out here. So now, this is still a right angle right here, isn't it? Which side is equal to 1 now, though? That's the radius. That equals 1. This over here is the tangent. And this distance up here is the secant of theta, both inside and outside of the circle. Still comparing that to this triangle, which I'll redraw. That's still theta. This is still the hypotenuse. This is still the opposite. This is still the adjacent. I look at the tangent. And now I'm going to compare it back to this side because that's the side that's equal to 1 in this triangle down here. So what side in the other triangle corresponds to the tangent side? The opposite side. What side in the other triangle corresponds to this radius of 1? The adjacent side. The tangent of theta is equal to opposite divided by adjacent. There is no secant there because this doesn't ever go outside the circle. So that's just the 1. That's just the radius. Yes. Yeah, well, the 1 unit is always just the radius. So this triangle, all of these triangles contain a radius somewhere. This triangle contains the radius of its hypotenuse right there. This triangle contains the radius of one of its legs down here. So if we look at the secant, what side of the other triangle corresponds to the secant? Hypotenuse. What side of the other triangle still corresponds to the 1? The adjacent. The secant of an angle is equal to the length of the hypotenuse over the length of the adjacent leg. Now, of course, this up here is the cotangent, and this is the cosecant, right? This one's going to be a little bit tougher to envision, but theta is now right here. Why? This is horizontal, that's horizontal. Parallel lines, those two angles have to be equal. Yes, the right angle's up here now. So the cotangent of theta over 1. This is horizontal, so that corresponds to the adjacent side. This is the 1 here now. That's vertical. It corresponds to the opposite side. The cotangent of theta is equal to the adjacent side over the opposite side. Cosecant of theta, this is still corresponds to the hypotenuse, but the 1 is now vertical, so that's over the opposite side. Those 6 trig functions you should have recorded somewhere. Okay, so with those in mind, let's look at some triangles here. I'm going to call this triangle A, B, C. It is typical to label the right angle angle C. The sides get labeled according to the angle that they do not touch. In other words, according to their opposite angle. Why would it make sense to label them according to their opposite angle? Well, because the biggest side is opposite the biggest angle, like we mentioned earlier. Smallest side is opposite the smallest angle. So the size of the side relates to the size of the opposite angle. So we'll call the sides small a, small b, small c. So we use capital letters for angles, small letters for sides. I'm going to put some links in here. Somebody pick a number between like 8 and 15. 11. So this is B is going to be 11. A is going to be 60. C will be 61. Yes, that does work out. Sine of angle B. Well, first of all, let's look at our sides here. Side C is which side? Yes, the 61, but what label? Opposite, adjacent. It's the hypotenuse. That's always the hypotenuse. If we're looking at angle B here, and I'm going to change my color slightly. We're looking at angle B. Sine, of course, involves hypotenuse, but what other side? Careful. Opposite. And if that's the angle we're looking at, angle B, the opposite side is side B here. That would make side A which side? The adjacent. So sine is opposite over hypotenuse. So that's going to be 11 over 61. So the sine of angle B would be 11 over 61. I've done this a few times before. So what if I ask you for the cosine of B? Yeah, adjacent over hypotenuse, 60 over 61. Tangent of B. Then we'll see opposite over adjacent. Secant of B. Yeah, hypotenuse over adjacent. Cosecant here of B. 61 over 11. Very good. Cotangent of B. 60 over 11. Good. Things to note. There's a link in cosine and secant. What's that link? Do you see it? They're flips. They're called reciprocals. How about sine and cosecant? They're reciprocals. They're flip. Tangent and cotangent. Reciprocals again. How about if I look at sine of angle A? Now, if I'm looking at angle A, this is not the opposite side anymore, is it? This is now the opposite side. This is now the adjacent side. The hypotenuse never changes. The hypotenuse is always across from the right angle. But the legs change depending on which angle we're looking at. So when I'm looking at angle A, this is the adjacent and this is the opposite. So the sine is opposite over hypotenuse, or 61. The cosine of A. 11 over 61. Tangent of A. 60 over 11. Secant of A. 61 over 11. Cosecant of A. 61 over 60. Cotangent of A, oops, 11/60. Now, some things to note here. Obviously, the cosine and the secant are linked again, aren't they? The reciprocals. And obviously, the sine and the cosecant are reciprocals. And tangent and cotangent are reciprocals. But even more significant here is this. What's going on there? The sine of B and the cosine of A are the same thing. Well, why? They're in the same right triangle, that's true. If I took A plus B, what would I get? This is right angle, that's 90 degrees. Triangle adds up to 180. So that leaves 90 for these two, right? A plus B are complements. And the sine of one is equal to the cosine of the other. The cosine of A, since it's a complement of B, is defined to be the sine of B. Does that make sense? If I tell you that the sine of 20 degrees is, I gotta calculate 0.324. What's the cosine of 70? Yeah, 0.324. The complement of 70 is 20. So the cosine of 70 is the sine of 20. It's defined to be the same. What do you think? Is it 342? I wrote it down wrong. You're right. 342. Same thing though. It's defined to be the same. The sine of one has to be the cosine of the other. Now let's look at our unit circle for a second. Again, it doesn't matter where theta is. Let's put theta up here. What the heck? What is the largest sine of theta could ever get? Or this is the sine of theta. Yeah, 1. Right here is its largest. That's the biggest sine, right? Sine will never be larger than 1. Now it could go down here and be -1. So the sine is always between 1 and -1. Are there any other functions that always stay inside the circle? There you go. The cosine of an angle will always be between -1 and 1. The secant always goes outside the circle, doesn't it? So it has the radius plus a little bit more, doesn't it? So the secant of an angle is always greater than or equal to 1 or less than or equal to -1. Cosecant falls in the same boat. It's always greater than or equal to 1 or, oh, dang, this pen is annoying me today, less than or equal to -1. How about tangent and cotangent? Yes, but can tangent be 0? If I have a really small angle, that tangent can be really small, right? If that angle is 0, the tangent's 0. Can it be almost infinitely large? Yeah. Tangent and cotangent can both be pretty much any value. So, I mean, there's a lot of things. The unit circle, if we see that unit circle, the relationships are just all right there. So many of the things that you memorized about trig come off of this circle. And we'll look at those relationships as we go through everything that we're going to do. Let's say that you are asked to calculate let's just say this, that's to find the sine of angle A. What would the sine of angle A be here? 6 over 10. Very good. What if I gave you another problem where I said the angle A is equal to 50 degrees? How would I find the sine of angle A? In other words, the sine of 50 degrees. On your calculator, hit the sine key, type in 50. You get 0.766. I want you to try that on your calculators right now. It's important that you give it a shot because there's modes on your calculators that have to be set right for this to work correct. I want to make sure you're in the right modes. Every now and then some of the calculators come set with a default of radian mode, so it really screws that up. How about if I ask you to find over here the cosine of angle A? Adjacent over hypotenuse, right? How about over here? Cosine of 50 degrees. 0.642, 643. How about over here, I asked you to find tangent of A. There you go, 6 over 8. Over here, I asked you to find tangent of 50. 1.192, we'll call it. Over here, I asked you to find the secant of angle A. 10 over 8, yes. Hypotenuse over adjacent. Over here, I asked you to find the secant of 50 degrees. That button's not on your calculator, isn't it? But remember from what we saw up above, the secant is the reciprocal of the cosine, right? Well, this is a different setup over here, right? Over here, it was 10 over 8. But over here, we don't know the sides of the triangle. It's 1 over the cosine of 50. So we can literally do 1 divided by the cosine of 50 degrees. 1.556. Remember, the secant's always bigger than 1, so that makes sense, right? Over here, if I ask you to find the cosecant of angle A, it's going to be what? 10 over 6. Over here, if I ask you to find the cosecant of 50 degrees, cosecant was the reciprocal of the sine. So it'd be 1 divided by the sine of 50. 1.305. Cotangent of A. 8/6, right? Over here, cotangent of 50. Cotangent is the reciprocal of tangent. So I can do 1 divided by the tangent of 50. 0.839. What do you think? Loads of fun? Yeah. Well, we'll look at inverse trig functions when we come back. For right now, you guys got some pages. Page 719, 722, 724. It is exercise 33-3, 33-5A, and 33-5.